Okay, so we are at the hardest lesson of this unit, which is solving torque problems. Now, we're going to kind of go over some of the formulas we're going to need because we're going to need several. These are going to be very similar to solving the force problems way back when. We're going to be dealing with pulleys because, again, since we are talking about torque, before we only talked about the acceleration of the masses whenever we had a pulley. Now we're talking about the torque being exerted on that pulley. Most of that are the cases that we're focusing on. Occasionally we'll focus on some other cases, but for this lesson, for right now, for the Edpuzzle, I really wanted to go over the pulleys because it's been a while, and we're gonna have to pull back some old information about how those situations worked with the force of the tension and the string and all of that. So let's go over some of these formulas we're gonna need. So think for a second. Again, I want you to look back over your notes or try and recall it, would be best. Before I give it to you. So Newton's second law for rotational motion has to do with torque. Look back over your notes. What was that formula? This was the fact that the net torque, which remember that means the sum of all the torque acting on a rotating object, is equal to its rotational inertia times its angular acceleration. If you want to write that in words too, I know we're still getting used to these variables, so we want to make sure we know what these variables stand for. Now, rotational inertia, now I will say this is the, remember, general equation for rotational inertia that if they don't give you a special one, this is the formula we use. The mass of the object. Now, this is going to get really confusing starting with these questions. This is referring to the mass of the rotating object, not an attached mass, which is what we're going to see in this case. We got to be careful to keep this straight. Where r is the distance from the center of the rotation. Now again, and especially actually in this lesson, we're going to be given some special formulas. If they say use this formula for rotational inertia, remember certain objects have more accurate formulas for their rotational inertia, but they will always give them to you in the question if they want you to use something different than this. If they don't give you something different, then we assume this is the formula. Now we have just torque in general as well. So remember, go back to your notes, recall what was torque. Torque is the radius. Now again, this is different. This is confusing. R specifically refers to the center of the distance from the center of the rotation of the object. This R specifically refers to the distance between the center of rotation and the contact point of the force. Remember that I can apply, even if I have a rotating object, depending where I apply the force to get it rotating, that will affect this R. Even if the object, like a door, again, we talked about even if a door is this long, if I apply a force here to push that door open versus at the edge, that's going to change this R. You just have to be careful. This specifically refers to the radius of the object itself or the length of the object itself from the center of rotation. This R refers to the center, to the contact point of the force. Be very careful to try and keep those straight. Now we're also going to have to do Newton's second law for linear motion because, like I said, we're going to be dealing with a pulley system, which is linear motion on the masses, right? We have rotational motion in the pulley, and then we have linear motion for the masses. So Newton's second law says that a net force causes an acceleration. So what's this formula? F net equals ma. Now again, we're going to have to keep this straight because we're going to be dealing with the mass of the pulley as well as the mass of blocks. Those apply differently, so be very careful. This mass here would be like the mass of the rotating object, the pulley. This mass would be the mass of the object pulling on the pulley. So we're going to need to make some use of subscripts for sure to make sure we keep all this straight. Now, when we attack these problems, as we recall, guys, it's been a while, like I said, since we've done this type of problem, really you always want to start backward. Start with your goal. So it's going to say, what is blah, blah, blah? And you write down, okay, this thing is question mark. And then we kind of want to work our way down and say, okay, what formulas do I have with this variable I'm trying to find? What concepts do I need to apply? Sometimes it's a good idea even to just jot down all possible formulas you could need and say, okay, let's puzzle this out. How do I put these formulas together to get me to my end goal? So we can kind of work our way down until we find a starting point. So let's go ahead and start off with this first one. This first one is going to be abstract in that there's no numbers. This is a very common thing on the AP test, and I want to do a little bit more of it, that your answer, we're going to get our answer here. I'm going to skip to the end here. In terms of F, M, and R. So our answer is going to be an equation for the angular acceleration of the pulley. So we could use this equation if we had numbers to get an answer, but I want to make sure we can get some practice with this. So we have a pulley is a solid uniform cylinder of mass M pulley. I'm going to go ahead and abbreviate that to just MP probably. And radius R that is free to rotate around an axis through its center. So here's our pulley. It's rotating, and there's our center of rotation. We have a lightweight rope, which basically means we're ignoring the mass of the rope, is wound around this pulley. We are going to pull down on the rope with a constant force, F, pulling down on the rope, which causes the rope to unwind and rotates the pulley. The rope does not stretch and does not slip on the pulley. They say this is just important to make things simpler. If the rope did stretch, this would be a much more complicated problem. So they'll say that. That just means we can make some assumptions about ignoring certain things. Use the formula. Okay, so here again, they're giving us a special formula for rotational motion for this cylinder. They're going to call this pulley a cylinder, rotating about its center. So anytime we need to use the rotational inertia, that's the formula we're going to use instead of the general one. So again, we want to write an equation for the angular acceleration of the pulley about its axle. So like I said, we're going to start from the end and then work our way down until we can kind of figure out a starting point. So here's the end. The end is, what's the angular acceleration? Right? That's our end goal. What is alpha? So now we need to look and think, okay, what formulas can I work with that use alpha? So think for a second, look to your formulas, and then we'll check. Well, we know that by Newton's second law for rotational motion, which is what a lot of these questions are going to be about, hint, hint, we have alpha right there. That's our angular acceleration. So we could possibly use this equation to get alpha by itself. But again, we are looking to get it in terms of F, M, and R. What that means is we're going to need to replace some of these other formulas. I really should write torque correctly. I always put it as a lowercase t. Remember, it's technically a small capital T, it's tau. We're going to replace with more formulas so that when I get alpha by itself, all of the variables that represent it in the equation are F, M, and R. So let's go ahead and replace then with our formula for torque. And then we're also going to replace our formula for I as well. So let's go ahead and let's look at the net torque acting though. Again, this is net torque. It's going to be simple to start with. We're going to look at some situations where we have multiple forces causing an object to rotate. That's going to cause several different torques we have to add together. In this case though, the net torque of the pulley is only caused by this force. So here's our radius of the pulley. The nice thing about these questions, most of the ones we're going to be dealing with, is that this is perpendicular. Remember, that means we're good to go. The torque formula, in the torque formula, this force is the one we want to use. If this rope were being pulled like at an angle this way for whatever reason, we would have to find the perpendicular component to the radius. But in this case, our force is perpendicular to the radius, so we're good. So this is the only force acting on this pulley. So when we look at the net torque, we have the radius. I'm going to do it as capital R because that's what they told us to use. It's capital R times just that force. Again, we may have to add other torques at working on this pulley, but in this case, it's just the one force. And so that's our net torque. And then we have our I, which again, they told us this is the formula we're going to use for this. So we have mr squared over 2 alpha. Well, great. Now we have everything. All of my variables are F, M, and R, right? F, M, and R. So all we need to do then is get alpha by itself and simplify. And there's our equation for the angular acceleration in terms of F, M, and R. So take a moment, go ahead and move over what you need to, and then some things are going to cancel, some things are going to simplify, so that we have alpha equals 1 simplified equation. Okay, what we're going to do is we're going to multiply by the reciprocal, right? Or however you want to do this. I'm going to go ahead and do it in one step. We should know that multiplying by the reciprocal on both sides, whatever you do one side, you got to do the other, cancels a fraction out, right? So the nice thing is that, hey, alpha is now by itself. That's angular acceleration. That's what we wanted. And now I am just going to need to simplify this. So pretty simple, actually. It's just the R that cancels one of these, right? So on top, we have 2 and F still. And then on bottom, I have the mass of the pulley and then just 1 R. Again, we had 1 R on top, R squared on bottom. And there's my answer. This is an equation in terms of F, M, and R for our angular acceleration. So again, what we did was we started with what we wanted to find. We figured out a formula that uses what we're trying to find. And then we went from there. Now, before we move on to another pulley type question though, dealing with angular accelerations in particular, we're going to go back to talking about tension in this string because the next questions we're going to be dealing with have masses instead of just a force. It's just a mass that attaches and then gravity pulls it down. So we need to, it's been a while since we've looked at this, so we're going to need to look back for a second before we move on to more types of these questions. So let's review this. We have a block of mass M, pulls a winded rope from a pulley. Again, we're making the assumptions that we can ignore the mass of the rope, that it's not slipping or stretching. We can do that. So what we want to do is write an expression for the net force acting on the block. So let's think about how we did this. It's been a long while. What we needed to do was draw a free body diagram. Net force, remember, is the sum of all of the forces acting on this block. So I want to see if you can recall this. Take a moment. There are 2 forces acting on this block. What are they? Well, we have the force of gravity, and then we have the force of tension. So I hope we recalled that one. So what we need to recall from here then is how I'm going to take this and write my net force equation. So my block is traveling downwards, but these forces are pulling in opposite directions. So think about how I'm going to write, putting these forces together. Because they're opposite directions, my block is traveling downwards. How did we do that? Well, what this means is force, if it's traveling downwards, that means the force of gravity is greater. And so we are going to call that positive. And I'm going to subtract force tension because that's pulling upwards in the opposite direction. Gravity pulls downwards. But again, we're going to call gravity positive because it's going to be greater since it is traveling downwards. Remember, if this block traveled upwards, that means the force of tension would be greater and we would switch these. So there we go. There is an expression for the net force acting on that block. Now, all we're going to do here is pretty simple, but we're going to take this expression and get force of tension by itself. If you recall, we had to do this a couple times. So go ahead and do that. Move stuff around and get the force tension by itself. Okay, so we have F net equals, why do I keep using my mouse? Fg minus Ft. So I'm going to subtract over the force of gravity. we have F net minus the force of gravity equals negative force tension. Don't forget about that negative, because this is just going to flip our signs. So to get our final answer here, this is going to become, we just switch our signs. Negative, positive, positive is how we can do that. So I'm going to rewrite this for our final answer. Force tension is now positive. I'm going to rearrange this. So force of gravity comes first because it's positive, and F net comes second. So here is an expression for force of tension. Real quickly, we're going to do it down here as well, but just to recall what our formulas were for force gravity and force net, because again, it's been a while. We should know the formula for force of gravity. What is it? It's mass times gravity, right? However, the net force, remember, Newton's second law, the net force acting on an object equals what? The mass of the object times its acceleration. This object is not accelerating at the rate of gravity because it's being pulled upward by the string, right? It's not just falling. So the acceleration of the block is going to be different than the acceleration of gravity. So that's why net gets the A and gravity gets the G. So we're going to keep this in mind for later, but again, technically this would be our final formula. Gravity, the acceleration due to gravity, I guess we should say. So the force of gravity minus the net force acting on it, again, is caused by that acceleration. Okay, let's look at another situation here where we have two blocks connected over a pulley. Now, again, we've done this before. We're going to kind of walk through the whole thing we did because we're going to need to do that sometimes. So we have two blocks connected over a pulley with mass 2 traveling downward. We are ignoring the friction acting on the table as well, on the table right now if there was friction. We're ignoring it. So let's go ahead and write an expression for the net force acting on mass 1. So before we do that, we need to draw a free body diagram. Take mass 1 and go ahead and draw on mass 1 any forces acting on it in the direction of motion, I will say. Okay, well, we just have force tension. Now, what I'm going to say here is this is force tension 1. What's going to end up happening, it's been a while since we had to do this. This force of tension is going to be different than this one because different masses are being pulled at different ends of the string. This pulley kind of acts as a stopping point for this force here to be different than this force here. So this is force tension 1, we will say. Now again, yes, there's also the normal force and the force of gravity, but because this block is not traveling in the y direction, we can know those forces cancel each other out and we can ignore it. It's not traveling in the y direction. So what that means then is write an expression for the net force acting on M1. So F net for block 1. Well, there's only one force acting on it, right? So the net force is just the force of tension on block 1. And that's it. There's no other forces acting on it that are causing it to move. So let's go ahead and go down to the next one. Now we're looking at mass 2. So we did this before, we just did it. Go ahead and draw an FBD for mass 2, and then write the expression for the net force acting on block 2 in the same way we did up here in this situation. Okay, well, we have the force of gravity, and we have force tension, whoops, why did I write it that way? Force tension 2. Again, this tension is going to be different because that mass is going to be different from on that side of the pulley. So it is traveling downwards, so force gravity should come first, minus force tension 2. Okay, so we are going to go from here then and see if you can recall how we answer these questions. Now, this is not, again, yet talking about rotational motion. We're going to talk about that more in class. We're probably actually going to stop after these slides, and then we'll do this one in class. But we've done this before. It's just been a very long time. We want to solve for the acceleration of the system. So remember, this is kind of funky. These blocks are going to accelerate at the same rate. It's just that, again, these forces will be different because even though they have the same accelerations, their masses are different, which will result in a different force. So let's go ahead, because since we're trying to solve for the acceleration, which is A, let's go ahead and rewrite both of these equations so we see A. Now, we don't know what the force tension is here, but we do know how to rewrite force net for this mass. Go ahead, and what should we rewrite right here? Well, this is mass 1 times its acceleration, but again, I'm just putting A because it's the same acceleration for both blocks, so I don't need to put A1 or A2. I do need to differentiate between the masses, so you have to be careful there. Here, let's do the same thing. I'm going to go ahead and we have minus Ft tension 2. We don't know what that is yet, but we can go ahead and also replace force of gravity and the net force. Go ahead and do that. Okay, so since this is block 2, this is mass 2 times the acceleration. Again, it's the same as block 1. And this is mass 2 times gravity. Okay, so we have these two equations here. We're going to kind of keep working with these to solve for A. Now, again, we are solving for A, but we do not have numbers, right? We just got variables. So our answer is going to be an equation. So coming from here, we're solving for the acceleration of the system. We have, let me make sure I'm doing this right. Can I do that? If those are different, we can get A by itself. Set those equal to each other, but I'm going to cut this part out. Let me see. Okay, so yeah, this is where I needed to. Oh, that's what I was doing. Oh, okay. So we would need to know that. Okay, then I might not. Okay. Okay, I lied. So I'm going to go ahead and actually, this is a question we would need that I didn't want to address yet. We're going to address it later, but I wanted to kind of do this in chunks, and I don't want to add that chunk on because it actually requires us to look at the torque, and I do not want to do that just yet. So we can, however, answer this last question, which would lead us to be able to answer those two questions that I just deleted. So let me see. Okay, so like I said, the reason why I wanted to kind of address this here is so that we can look at just this small piece and then add on the concept of torque. Since it's been a while since we've done this, we kind of wanted to be careful with that. Let me see here. Okay, so the last thing we're going to talk about here is what is the net force acting on the pulley causing the torque. So, because remember that torque net is caused by these different forces acting on the pulley. There are two different forces acting on the pulley, right? We have force tension 1 and force tension 2. Now, the nice thing about them is that they are both the same distance from the center of the circle. So we can look at them as having the same R, and we can just kind of look at those two forces with having the same R. So notice that one force tension is pulling backwards. Yes, even though the block is moving forwards, that pulley feels the weight backwards of that mass versus feeling the weight this direction. So since these arrows are pointing in different directions, most importantly, they're pointing different directions clockwise and counterclockwise, right? This direction is pulling clockwise. This direction is pulling counterclockwise. What that means is the net force acting on this, we're going to need to subtract those two because they are pulling this pulley in different directions. So think for a second again, based on the way this pulley is traveling, which way are we going to subtract? Well, this is going to be a greater force because the pulley is going to be rotating this direction, being pulled downwards and clockwise. So we're going to call that, we'll say the force tension 2 minus force tension 1. So just to kind of, again, we're going to address this in class, but that means that the net torque acting on this, which is normally just RF, well, they have the same radius. I really didn't mean to capitalize that. These forces are acting the same distance from the center, so we can just say R. Because they're acting the same distance from the center, that's why we can do this. This is the net force then acting on the pulley. Therefore, this is the net torque. We're going to come back to that later in class. I wanted to, again, just have you guys watch the video, review some concepts, and then we'll practice some more together.